morning everyone. Today we will be presenting our mechanism sessional project on the windscreen wiper mechanism. This work was done by me, Aryan Malhotra, and my teammate Nikhil Kumar Prasad. We'll walk through the classical 4-bar wiper mechanism, our simulations, and the innovations we have implemented. We'll begin with the problem statement, then look at how a windscreen wiper works. We'll show a working demo of the mechanism, followed by Grashoff's criterion used, and our displacement, velocity, and acceleration analysis of the mechanism. Next, we'll discuss the MATLAB simulation and finally highlight the innovations and improvements that we added to go beyond the original problem statement. The original problem asked us to synthesize the windscreen wiper mechanism. There were a few important requirements. First, the mechanism must not have a quick return effect, meaning the forward and backward strokes should be symmetric, which we demonstrated using graphs during our MATLAB simulation. Second, the simulator must clearly mark the wiped area on the windshield. And third, we were asked to add new ideas, which could include adjustable wiping range, determining wiping speed, and acceleration variation for a constant motor speed, or estimating the motor torque requirement, neglecting dynamics. This we have discussed towards the end of our presentation. A windscreen wiper is simple but an elegant mechanism that converts constant rotary motion from a motor into oscillatory sweeping motion over a windshield. Most cars use a 4-bar crank rocker mechanism where the crank rotates continuously and the rocker isolates. The performance of a wiper is driven by a few key parameters: the sweep angle, wiping uniformity, blade pressure, and how the wiping speed varies as the mechanism moves. Understanding these kinematic relationships is essential for designing a smooth and effective wiping motion. Now we'll demonstrate a working demo of the project on a website that we made. This is a working demo of our project on the website that we have created. This is how the mechanism works. You can fiddle with the speed over here and the positioning of the mechanism on the screen. This is a 2-wiper mechanism which we have created on the basic fundamental principle of the mechanism that was provided in the problem statement. Here is the basic calculation used. This is the MATLAB code which we will later demonstrate in the presentation, and these are the fundamental concepts used to create this mechanism.
Hello, my name is Nikhil Kumar Prasad. I will be presenting the further analysis of our mechanism. I will begin with the Grashoff criterion because it determines whether the mechanism can produce continuous rotation. For the given 4-bar mechanism, the link lengths are as shown. Grashoff requires that the sum of the shortest and longest links must be less than or equal to the sum of the remaining two. A short check shows that the condition is satisfied here. This confirms that the mechanism is a Grashoff mechanism and allows continuous rotation of the crank. Let's begin the displacement analysis part. The displacement analysis gives the relation between the input angle θ2 and the output angle θ4. We first assign the lengths to the links, and AD is the ground link. DE is an extension of link CD which connects the mechanism to the wiper XY. We then use the distance formula to calculate BC and then L3. The equation is transformed to A sin θ4 plus B cos θ4 is equal to C, with A, B and C as shown. We proceed by simplifying the equation to a quadratic form and then finding its roots, which gives θ3 and θ4. This completes the displacement analysis part. Moving to velocity analysis, it provides the relation between the input velocity θ2 dot and the output angular velocity θ4 dot. From Arnold-Kennedy's theorem, we can say that when three bodies are in relative motion, they must have collinear instantaneous centers. As L1, L3 and L4 are in relative motion, I13, which is the instantaneous center between 1 and 3, must lie on line AD. Similarly, as L1, L2 and L3 are in relative motion, I13 must also lie on the line BC. This means that I13 is the intersection of lines AD and BC. Proceeding with further calculations and using the concept of instantaneous centers, that the velocity of x as seen from the extended parts of both L1 and L3 is the same, we finally get that θ4 dot is equal to j times θ2 dot, where j is defined as shown. Now moving to the acceleration analysis part, it's quite straightforward. Acceleration analysis provides the relation between the input and output accelerations. Differentiating the result from velocity analysis and making some adjustments, we get the acceleration analysis results as shown. Let's move to the MATLAB simulation of this mechanism. First, we coded a windscreen wiper mechanism with a single cleaning blade. This MATLAB script models and animates the wiper mechanism. It defines link lengths, computes kinematic angles for a rotating input, and generates the wiping patches. The key parameters are defined and the input runs for 10 rotation cycles. For each input angle, the code solves closed expressions for θ3, θ4 and θ5 using trigonometric identities and then half angle formulas. θ5 is shifted so that the wiping arc starts when required. The code compares tangential speed from angular velocity with the computed linear speed as a check. The script builds wiping curves and a semi-transparent patch representing the wiped area. It creates a 2D animated figure with a moving bar skeleton as shown. Frame rate defaults to 30 fps. We get 3 plots of speed and velocity components and an animation of the wiping surface and mechanism motion. Next, we upgraded the original wiper model by adding a second independent wiper to increase the coverage and realism. The script reuses the original 4-bar geometry and kinematic solver. Key link lengths remain the same. A second wiper pivot is placed 900 units to the left of the first wiper pivot. Both wipers use the same computed θ5 sequence, so they move synchronously, but each has its own pivot offset and its own swept area patch. Wiper 1 uses a light blue patch, Wiper 2 uses a warm peach patch. Both patches are semi-transparent, so the overlap is visible. This mechanism doubles the wiped area, exposes interaction where patches overlap, and gives a realistic 2-wiper simulation for vehicle-style operation. That is the upgrade we made. Now I will outline the innovations we proposed. We built a dual wiper setup with pivot spacing of 900 units. This replicates an actual 2-wiper system instead of a simulated single arm. Second, we generated 2 separate swept area patches. Both the upper blade and the lower blade are tracked accurately, so the wipe pattern is not an approximation but a precise footprint. We can also add sweep alignment correction using angle shift compensation. Further, we can model the full blade geometry with a certain offset. Finally, we can animate the complete 4-bar linkage. This makes the structural behavior clear and avoids ambiguity, which you get when only the wiper tip is shown. Thank you.